So this is our final lesson in Unit 910. We've talked about rates of change, we've talked about limits, and finally we are going to talk about derivatives. And by the end of this lesson, we want to understand what a derivative is, what we mean by that term derivative, and we want to be able to use the first principles definition and our knowledge of limits to find the value of the derivative to a function at a particular x value, and the function that gives the value of the derivative at any x value. So let's just take a little recap of what we have been doing in Unit 910. We started with rates of change. We talked about the average rate of change, and then we used the average rate of change to figure out what the instantaneous rate of change was. And we did that by setting up that table and looking for the trend. And I told you that what we were really doing when we set up that table and looked for the trend was we were taking a limit. Okay? The instantaneous rate of change was the limit of this series of average rates of change as we made our time intervals smaller and smaller. We represented both of these things graphically. The average rate of change was the secant line between 2 points on our curve. The instantaneous rate of change we could represent by the tangent line at a single point on our curve. And then we talked about this thing called the tangent problem, where we had this big problem in calculus where we wanted to be able to find the tangent to a curve at any point. And then we veered off and we talked a little bit more about limits. And we said, okay, we can evaluate limits using a table, using graphs. And then we went and said, well, we don't want to mess around with tables and graphs all the time. So let's figure out how we can do this algebraically. Okay. Well, what we want to do now is we want to kind of circle back, and we want to take these techniques of evaluating limits algebraically and apply them to this problem of finding either tangents or slopes of tangents or instantaneous rates of change. And that's what brings us back to the derivative. Okay? So what is a derivative? A derivative is basically the answer to the tangent problem. The tangent problem was, how do we find the slope of the tangent, or how do we find the instantaneous rate of change given some function at some point? Well, what a derivative is well, the derivative of a function f at x at some point, p, with an x value a, represents one of two things. We can think of it as the slope of the tangent to our function f at x at this point x equals a, which we also call point P. So if the tangent problem asks how do we find the slope of the tangent, the derivative is the thing that finds the slope of the tangent for us. And we can also represent the slope of the tangent, of course, as the instantaneous rate of change. Of this function, f at x, again, at this specific point, we'll just call it point P. So our function doesn't necessarily have the same rate of change everywhere. We're looking for the rate of change or the slope of the tangent at a particular point. And as I said before, we're going to look at two things in this lesson. We will look at how to find the value of the derivative of a function, so the slope of the tangent or the instantaneous rate of change, at a particular point if we have a particular point that we are interested in, some value in here for a, where a is just some number. But then we're going to look at something that is a little bit more useful. We are going to come up with a function called the derivative function, which is a function we can use to calculate the value of the derivative for any x value that we put in. Okay? So if we got a bunch of different x values, we want to find the slope of the tangent at all of them, we can find this function, and then we just plug our numbers into the function, and it spits out what the value of the derivative is, or the slope of the tangent is. And we use this symbol here for the derivative function. It doesn't look very good there. It's f primed at x. Okay, so if our original function is f at x, our derivative function is f primed at x. You'll also see notations like y primed or dy dx. All of these are used to represent the derivative. So let's take a look at this first one here. How do we find the value of the derivative, or the value for the slope of the tangent at a particular point? So let's start by imagining that we have some function. F at x. We've got some particular point, some particular x value, where we want to find the value of the derivative. So this is a point on our function. Right here, this is that point P we were talking about before. So if the x value is a, the y value is going to be f as a function of a. Now we said before that if we wanted to find the slope of the tangent, what we were going to do was we are going to take the limit of the slopes of our secant lines as, well, as we did what? Well, to make our secant line, we picked another point somewhere over here. And I'm going to call this point x. Okay? So we took another point on our graph. We drew the secant line between a and between f, these 2 points on our curve. Okay? Our y value here is going to be f at x. Okay? And then we took the limit of the slopes of these secants as we moved x closer and closer to a. So we made these secants appear more and more like tangents. So we'll do this limit as x tends to a. So just writing this out, we're taking the limit as x tends to a of the slope of our secant is just going to be change in y over change in x. So f at x minus f at a all divided by x minus a. And we evaluated this using a table. Okay? And we'll say that this is our derivative f primed at a. Okay? So we did this using a table. What we're going to do this time is we're going to do it using everything we know about how to do limits algebraically. Okay? So let's just do an example here. We're going to find the derivative of f at x equals x squared plus 2 at the point x equals negative 3. So negative 3 here is our a value. Okay, we've got a specific point that we are interested in. So our answer here is going to be a specific value of the slope. At the end. That's weird. Let me just fix that. Specific value of the slope. And we're going to use that definition that we had on the last page. So f primed at a is going to equal the limit as x tends to a of f at x minus f at a all divided by x minus a. So in this case, our a value is -3. So we want the limit as x tends to -3 of our function f at x minus f at -3 all divided by x minus -3. Now, we can figure out what f at -3 is. We just take -3 and we plug it into our function, x squared plus 2. So that's going to be -3 squared plus 2. -3 squared is 9. 9 plus 2 is 11. So we want the limit as x goes to -3 of our function, f at x is x squared plus 2 minus, we just figured out that f at -3 was 11. And down in the denominator, we have x minus -3, which is just x plus 3. And then we can simplify the numerator a little bit here. Limit as x goes to -3. I have to keep writing limit as x goes to -3 because I haven't evaluated that limit yet. It's not until I actually do that substitution step that I can stop writing that. We'll still have our x squared. Positive 2 minus 11 gives us -9 over x plus 3. This is the limit that I want to evaluate. Now, we learned a couple of techniques for doing this algebraically. The first thing we always try is direct substitution. So we try to substitute -3 in there for x. And what do we get when we do that? Up in the numerator, we get -3 squared, which is 9, minus 9, which is 0. And then down in the denominator, we get -3 plus 3, which is also 0. So our limit evaluates to 0 divided by 0. We don't like this. 0 divided by 0 is something that we can't really work with. So what do we need to do here to evaluate this limit? Do a difference of squares. We're going to factor that numerator. So limit as x tends to -3, I'll get x minus 3, x plus 3 up in my numerator, all divided by x plus 3. And now I can see that these x plus 3's are going to cancel out. So I'm left with the limit as x tends to -3 of x minus 3. This is something I can evaluate by substitution, so I'm going to go ahead and do it. I'm no longer taking the limit, I'm evaluating the limit by subbing in -3 for x. -3 minus 3 is -6. So there we are. Okay. This is the value of the derivative for our function x squared plus 2 at the point x equals -3. So what does this represent? Well, this means that the slope of the tangent to x squared plus 3 at x equals -3 is -6. Okay. So the tangent problem says, hey, how do we find the slope of the tangent to this curve at some point? We've just answered the problem for this function at this point. Okay. So that's pretty familiar, I think. We've basically just done the same limit that we were doing before, but we did it algebraically instead of using a table. Now, I said more useful than just being able to find the derivative at one specific point is being able to find the derivative function. Okay? So we can follow a similar procedure to get the function that lets us calculate the derivative wherever we want. So, derivative function. This will work for any value of x. Again, we're going to imagine that we have some function f at x that we want to find our derivative for. We are going to pick some value. And I'm going to use x here because we don't know ahead of time what that number is going to be. Okay? We want to keep that general. We want to be able to calculate the slope of the tangent for any x value that we plug in. So x is going to be the point where we want to find the slope of our tangent. So the y value at that point is just going to be f at x. We're going to do the same kind of thing we did before. We are going to find an expression for the slope of the secant to this curve. Now, how are we going to do this? Well, what we're going to do is we're going to start at this point x, and we're going to move a short distance away from it. Okay. And I'm going to call this distance that we move h, because I got to call it something, right? So this distance h. So if we start at x and we go over a distance h, we've got this new point x plus h that we're interested in. And if we go up to our function here, we can find the y value, which is going to be our value of our function at x plus h. So f at x plus h. Same thing we did last time. We're going to find the slope of the secant between these 2 points. So the slope of our secant here is going to be f at x plus h minus f at x all divided by x plus h minus x. So same old change in y over change in x that we were doing before. Now, can we simplify this a little bit? Yes, we can. Because down in the denominator, we've got x plus h minus x. So we can simplify this. We keep the numerator the same, f at x plus h minus f at x, all over h. So that's the slope of our secant. Now, to find the slope of our tangent, we are just going to take h and make it smaller. If we make h smaller and smaller, we're moving these 2 points closer and closer together. So our secant lines become more and more like a tangent line. So our derivative function I'm going to call this f primed at x is going to be the limit as h goes to 0. Okay. So as we make h smaller and smaller, we're taking the limit of the slopes of our secants, which are given by this expression that we just came up with. F at x plus h minus f at x all over h. Okay. And I'm going to put a red box around this. This is what is called the first principles definition. And this is like the theoretical foundation that all of calculus rests upon. Okay? The fact that you can figure out what the derivative function is, or the derivative to a function is, using these limits lets us do calculus. Ironically, they could do calculus before they figured this out, but they kind of made it up as they went along. And the mathematical community was very nervous about calculus because it didn't rest on a very firm theoretical basis. Once they figured out you could justify everything this way, people were a lot happier. So let's see how we actually use this to find the derivative of a function. And again, we'll do an example here. Okay? Again, we're finding the derivative function, or the derivative of a function, at any point that we choose. So we want to determine f primed at x, that derivative function, from first principles, if the function we are given is x squared minus 3x. Okay, so our answer here, when we get to the end, won't be a specific value of the derivative, or a specific value for the slope of the tangent, or a specific value for the instantaneous rate of change. It'll be a function that we can use to calculate all of those great things. And the definition that we're going to use, of course, is that first principles definition from the previous slide. F primed at x equals the limit as h goes to 0 of f at x plus h minus f at x all over h. So how do we do this? Well, we've got f at x plus h and we've got f at x. Let's take both of these expressions and apply the function that we are given to them. So when we're asked to do f at x plus h, everywhere I see an x in f at x, I'm going to replace it by x plus h. So that first term in the numerator is going to become x plus h squared minus 3 times x plus h. And then from this, I'm going to subtract, well, f at x is just my function here, x squared minus 3x. I like using the big square brackets because they keep everything organized there. I know that my first square brackets are f at x plus h. My second set of square brackets are f at x. Next up, I want to start trying to simplify this. Still taking the limit as h goes to 0. In this first big square bracket here, I can expand that binomial to get x squared plus 2xh plus h squared. I can distribute this negative 3 to both of those terms in there to get negative 3x minus 3h. And I can also distribute this negative sign here to every term in this second square bracket. So I get negative x squared plus 3x. And if I've done this expansion correctly, we should see some of these terms start to cancel each other out. I've got an x squared here and a minus x squared over here. I've got a minus 3x right here. I've got a plus 3x over here. So I expand those out, and then I simplify. So I'm still taking my limit as h goes to 0, but now I've got 2xh plus h squared minus 3h all over h. This is the limit that I want to evaluate. Can I evaluate this limit by substitution? I sub in h equals 0, I get 0 in the numerator divided by 0 in the denominator, which is a bad thing. But I can factor the numerator. I've got an h that is common to all of those terms, so I'm still taking the limit as h goes to 0. Let's factor out that h. 2x plus h minus 3. Okay, so h times 2x plus h minus 3, all divided by h. And then I can cancel that h out in my numerator and in my denominator. So limit as h goes to 0 of 2x plus h minus 3. So now I have something that I can evaluate by substitution. So I'm going to sub in h equals to 0. I get 2x plus 0 minus 3, which gives me 2x minus 3. This is my derivative function. Okay? F primed at x equals 2x minus 3. What does this function do? Well, it gives me the slope of the tangent to my original function, x squared minus 3x, at any x value that I choose. So if I said I want to know the slope of the tangent to x squared minus 3x at x equals 7, I can just evaluate f primed at 7 using this function, 2 times 7 minus 3. So the slope of the tangent would be 11. Okay? If I wanted it at a different x value, I just choose whatever x value I want, sub it in, it tells me the slope of the tangent. Okay? So this is where we're going to be going in the next units. We are going to be looking at how you take different classes of functions and how you find the derivative function for each of them, and how you can use that to solve problems where you need to know the slope of the tangent or the instantaneous rate of change. But for now, we're just going to use this first principles definition.